Well, of course, I will start by saying I was very honored to be invited, first of all, for this series online. And of course, I'm very excited to be here. I have a pretty broad title that I put on there, but I'm actually going to talk about something much more specific. I mean, the work that I'm going to talk about here is, coming out of a larger body of work that I've been working on the last few years on basically trying to solve constrained optimization problems with stochastic algorithms, essentially motivated by machine learning type problems and really maybe sort of more informed learning, where you basically try to impose prior knowledge through constraints. People call hard constraints as opposed to soft constraints where you're just using penalties, but actually solving constrained problems where the constraints are handled as constraints, basically what we do in deterministic optimization and some of the best algorithms there. So a lot of the work that we've been doing is on essentially Newton-based SQP type things, and we have various papers and extensions, but this time I'm going to talk about an interior point method. And I'll try to motivate why we're doing that, and I'll also try to explain some of the challenges that have come up along the way that I think are somewhat interesting. So this is coming out of a work that with myself, Slava, Daniel, and my student Chi. And Chi is the one that I would say did the heavy lifting, and she proved things that I didn't even think were possible, and we'll see some pretty intricate, I'll try to make it simple, but some pretty intricate complications that come up that she was able to figure out. And we have another working paper with my postdoc Shin that's in development. Okay. So I want to talk about an interior point method, and again, it's going to be motivated by a stochastic setting, but I'll start with deterministic, called SLIP, single loop, and I'll explain what that's all about. I'll give you an analysis for the bound constraint setting, and then we'll generalize it or talk about how it gets complicated for the more generally constrained setting. So, I come from a group where, for constrained optimization, interior point methods are sort of seen as the best kind of algorithm in practice for a large variety of problems. So some of the best codes like IP Opta Nitro for those kinds of things are very successful. I put this bold statement about no stochastic interior point methods. If anybody knows differently, I'd really like to hear about them. But basically, interior point methods where you assume that your objective gradients are only stochastic. I haven't seen work on this. I saw there's one paper, but it has a pretty serious flaw in some of the proofs. And I'll try to explain why. Basically, it failed to handle the fact that the barrier function doesn't have Lipschitz gradients and things like you would normally need. So why is this? Well, first of all, stochastic algorithms for constraint optimization haven't been looked at so much, and there's a caveat for that, of course, because there's actually a lot of types of algorithms that do this but usually they're dealing with very specific types of constraint sets, like bounds where or at least sets that you can project onto, or you're working on manifolds, or you're doing things where conditional gradient methods where the constraints are can be handled in a very structured way, as opposed to where we eventually want to go with this and what we've been doing with our SQP work, basically general, nonlinear, non-convex constraint functions and things like that. That's where we want to get to. Another reason why I think people haven't looked at interior point methods is that there just ends up being some tricky things and you don't necessarily need them. So if you're doing like a bound constraint problem, like I'm going to talk about, you can do like projected stochastic gradient, and then you can get all the convergence and nice things to work there. So why would you even bother doing interior point? Okay. So especially with all these extra complications that come in, but I'll show you that actually it seems to work pretty well. That sort of motivates. So I'm going to talk about the bound constraint case and then move on to the general constraint case, as I mentioned. So here's some notation. Bound constraint optimization problem. My objective F, I'm going to assume, is smooth. But it could be non-convex. So we're looking for some kind of first order stationary point, point satisfying these optimality conditions here. We can handle infinite bounds, but I don't want to get into all the algebra with infinities and things, so we'll just assume that we have finite bounds. This is the sort of textbook interior point method. You basically take for nonlinear constraint optimization, take a textbook interior point algorithm. This is what it looks like from like Nosedal and Wright or something like that, where you say, okay, I have my I'll call it a barrier augmented function, your little objective plus your barrier terms. You basically have a two-loop process. It's not written that way, but that's basically what's going on here, where you have a fixed barrier parameter. You minimize this function to some accuracy until you get, say, the gradient with respect to x below some threshold related to the barrier parameter. Once that happens, you would reduce the barrier, otherwise you would leave it fixed. You basically have a fixed barrier, minimize this function to some accuracy, and then you would decrease the barrier and so on. And in the inner loop, you're basically just doing a descent type algorithm. Compute some kind of descent direction. This is just like a first order step, but obviously you could do, second order or whatever. And the key thing that happens there is something called a fraction to the boundary rule, where you stop yourself from going too close to the boundary too quickly, and that what you can essentially show is that if you slow your movements to the boundaries enough, eventually the barrier will push back, and that you don't have to worry about going too far into regions where the gradients and the barrier blows up. So that happens in the sort of textbook kind of algorithm here. Then you do a line search or whatever. We want to go to eventually the stochastic setting here with stochastic gradients and so forth. And there's a few things that we would have to address. First of all, this sort of two-loop structure becomes problematic. Even just checking the stationarity measure becomes an issue because you assume you can't necessarily compute this gradient, just a high accuracy. You could think about estimating it, and then you decrease the barrier parameter with maybe when you have a good, idea that you're relatively stationary, but then you end up having this outer loop with the probabilistic guarantees, and maybe you did it wrong sometimes, and that becomes a little bit tricky. Another thing that's an issue is this fraction to the boundary rule. When you start to tie decisions of the algorithm to your iterates, then doing the analysis and even what you expect the algorithm to do in practice becomes a little bit tricky. And finally, of course, you have to deal with these unbounded gradients, lack of Lipschitz continuity of the gradients, and so on and so forth. I'm going to get back to this picture a little bit later as well. So our idea is a new algorithm. It ends up being a very simple kind of algorithm, but very, I would say, intricate to analyze. So the first idea that we do is probably what you would say, oh, maybe this will work. Just decrease the barrier parameter by at a prescribed rate, rather than have this check of, okay, we've gotten sufficiently optimal, now I'm going to decrease the barrier parameter. That's obviously a simple idea. How is it going to work though? Well, that ends up being where you have to make sure you don't get too close to the boundary too quickly relative to your current barrier parameter. And so the thing that we did is we introduced this neighborhood sequence. So we're going to, in addition to prescribed sequence for the barrier parameters to decrease, we're going to have this neighborhood parameter sequence, we call it, this theta. And in every iteration, we're going to enforce that we stay far enough away from the boundary. And you can imagine in the analysis, there's a very important relationship between these two sequences and how the rates of decrease and so on and so forth. So we end up doing things that you'll see, it's kind of like a projection inside of the algorithm. So I mean, and the algorithm ends up being computationally very similar to a projected gradient type method, but it is following, or at least the idea is it's going to try to follow some kind of central path, at least in the convex case. I will just say, probably some people would look at this if you're familiar with interior point methods and say this sounds sort of nuts, right? I mean, interior point methods. It came out of, basically trying to obtain good complexity properties. And you would try to follow a central path, and you'd get, once you're sufficiently far along getting onto the central path, then you can do like one step of Newton's method and basically converge where, mu is dropping very quickly. This is not like that, right? This is totally, different. This is going to be a mu sequence that's decreasing at a sublinear rate and all that. So why would you even think about it? Well, our experiments say that this is worthwhile. So I'll just show you a simple experiment that we did. This is a logistic regression problem and then like a one-layer neural network with cross-entropy loss on standard data sets. So just as basic. What we're showing here is per problem, and these are ordered so that the plot looks nice. This is a relative performance, and basically down means the relative improved performance for the interior point method versus the projected gradient method. This is for, yeah, like I said, logistic regressions to a convex case, a little bit of a non-convex case here. And besides one problem over there, I mean, it's outperforming this projected gradient algorithm. And why would it do that? Well, I mean, I don't know. To me, projected gradients is basically you're trying to get along the wall and you're just banging your head along the wall and as you climb around, versus an interior point method that could, ideally curve nicely into the corner over there. So, I mean, will this always be better? Is it always worthwhile to do this crazy kind of algorithm here? I can't promise that, but at least what we see is that there's some motivation to look into the analysis and see if we can get it to work. So I'm going to start with a simplified version of the algorithm and then try to explain to you the complications that arise in the analysis, and then in the stochastic case, I'll make it a little bit more general. So this is a simplified version of what we actually analyzed in the paper. It ends up being very similar to what you would probably expect. You start with some descent direction. Let's just say negative gradient, but really, if you have the barrier, then you could use the Hessian of the barrier and all that. But let's just say some descent direction. A step size, where if you're thinking about stochastic gradient or gradient type algorithms, this looks like a 1 over L type step size, and this is basically a quantity that comes out of the barrier function. So this looks like a 1 over Lipschitz constant type result. And then the key thing, though, is this gamma you choose to make sure you stay within this neighborhood. So basically, don't get too close to the boundary too quickly. It's kind of working like that fraction to the boundary rule, except now it's by this prescribed theta sequence. Right? So a very simple algorithm. But of course, what you have to make sure is that this, if you just had to deal with descent steps and step sizes like this, things you'd expect to work. But when this gamma comes in, you're shortening your steps. You could not necessarily make sufficient progress. So that's the thing you have to worry about in the analysis. So a few important observations along the way. One is that even though the barrier function that we're essentially minimizing, although it's changing while we're minimizing it, this is what the algorithm works with. But really, we can do the analysis in terms of some sort of scaled barrier terms, where this is important because for this function, which has the same gradients as this one, it's just a shifted version of it, when we decrease mu, it also decreases this function as opposed to this one. We make a slight assumption here that there's some constant sufficiently large that these are between 0 and 1, but this is a pretty mild assumption, I would say. In general, the algorithm doesn't even need to know this value. We just assume that it exists. Yep. It's just shifted basically by a constant. Yeah. Yeah. No problem. Okay, so what you end up seeing is because we keep ourselves in each iteration within this neighborhood, we're at least going to have Lipschitz continuity and so forth of the gradients over the path that the iterates are taking with respect to values that are occurring in that given iteration. And so you still have like an upper bounding type by a quadratic that you normally have for this function phi tilde here. And if you choose the step size sufficiently small, you expect to get this kind of decrease. Where the important thing is that this decrease now, by the way, this is deterministic first, right? So we'll get to the noise in a second. This is what you would normally expect to see, but the difference, of course, now is we have this gamma, where this gamma is forcing us to stay within the neighborhood. And so really what we need to make sure of is that this gamma times alpha doesn't go to 0 too quickly, so that we maintain sufficient decrease. And so what we see here and what we were able to prove is that gamma k is bounded below by a quantity that looks like this, and obviously it gets a little bit complicated in terms of the mu and theta sequences. But what we were able to show is that if you decrease mu and theta at a rate, and one thing that's allowable here would be something like a 1 over k, so that's the typical thing that you would see in gradient descent with diminishing step sizes, is that when you do this, you can prove that this gamma alpha is unsummable, which is the kind of thing that you would want to be able to say that you're getting sufficient decrease, and basically the convergence falls out from here. There's an additional thing here in terms of keeping this quantity bounded. That ends up being important to be able to say things like, if you have an infinite subsequence that converges to a primal point, that there exist multipliers that give you primal dual stationarity. Okay? So this is the main idea of the algorithm. Why does it work? Well, in my mind, this is the simple reason why it works. And it's all having to do with the rates that we're decreasing this barrier and neighborhood parameters. Is that on a given iteration, xk is within the theta k minus 1 neighborhood. So this is the zero boundary, let's say. So let's just say x is being non-negative here. Xk is over here somewhere. Even if it's at the worst case where the gradient is the steepest for the barrier, let's say here, so this would be the red is the sort of tangent line for you can see the steepness of the barrier term only. When we take the step to go to the next iteration and then we update mu, we find that the gradient does not blow up. So basically, by having the barrier parameter and this neighborhood parameter tied together, as we step closer to the boundary, there's still going to be a uniform bound on the norm of the gradient. And that's what allows us to slowly, move towards the boundary without the barrier blowing up too much. And that's the essence of how it all works. All right, so the stochastic setting, it gets obviously a little bit messier. And what I think is particularly interesting is that we can't use, although we can get arbitrarily close to, we can't use the same kind of sequences that we can use in the deterministic setting. We have to restrict them a little bit further. Yeah, Steve. So in even just here in the deterministic setting, the answer is not enough, because you think about it, the barrier would only act in a reactionary way. You would get too close to the boundary and then it would push you away. So it would, at least we couldn't figure what. Yeah, preemptive so that we can make sure that in every iteration we're getting. There may be more complicated ways of doing the analysis that you would allow yourself to get too close, and you can keep track of iterations where that happens and bound those things. That might be possible, but we didn't find a way to do that. So it's preemptive. Yeah, it's preemptive. Okay, so in the stochastic setting, and then there's a caveat here. So here in the stochastic setting, what I mean is that our estimate, or what we're going to be using for the gradient of the objective function, is just going to be an unbiased estimate, some bounded variance, noise assumption. Unfortunately, what we were only able to accomplish, although I still think it's interesting and a lot, we do need to actually know a bound on the noise. We need to have bounded noise. We'll still have a unbiased estimate, but it needs to be bounded. So I really wish that we could have gotten away with that, but anyway, that ends up being a part of it, but I still think it's all useful. For the deterministic setting, we can do a nice choice like I was saying, 1 over k for the mu, 1 over k for the theta, and then if you plug that in, what you see here is also like a 1 over k for this alpha step size. It turns out, though, that for the stochastic setting, even with this bounded noise assumption, we can't do that anymore. We actually have to have the step size sequence decrease a little bit more slowly, although it can be arbitrarily close. And of course, it'll be a little bit difficult to show you all the details about that, but I'll try to motivate at least why. And it comes down to this type of inequality that you see in stochastic gradient type methods, where you're trying to show, the x's now are, from a stochastic process, so they're capital XKs. The normal thing that you would see the decrease now is there's this term that's sort of coming from the current stationarity measure, but then there's these noise terms. This is one that basically an expectation, will be fine, but this is the one you have to deal with in terms of bounding the noise. And it turns out that because you have the alpha and gamma here, this A is the capital alpha and capital gamma, where the Lipschitz constants are also increasing as you get closer to the boundary, that you are not controlling this term enough with those choices. So you have to make the step sizes go a little bit smaller in order to compensate for this blow up of the Lipschitz constants as you approach the boundary. Yeah? Yeah, so we throw in here some generic HK. In practice, we would use something like, you could be like the identity plus the Hessian of the barrier, if you have some estimates for the Hessian of the objective as well. In the paper, it really just needs to be, actually in the paper, we kept it simple as a diagonal, it's acting as a kind of Hessian. Bounded and from below and above in terms of eigenvalues and things. Yeah, sorry. So then that ends up being h, minus 1 norm and so on. But really the key point here is this. And so it ends up being obviously a little bit complicated in terms of the step size choices. And the reason we need to know the noise is then we have this this gamma k. We also need to bound that. So obviously I'll be happy to talk to anybody more who is interested about the details of this. But it's essentially the same algorithm. We just need to control the step sizes a little bit more. And we may even also need to restrict the gamma k's further within the algorithm so that we are compensating for this extra noise. But I'll just try to show you graphically about this selection of all these parameters. So basically, if you want to think generically, you could think of mu k is like k to the tau mu, and theta k is like k to the tau theta, and so on. In the details of the analysis, you realize over time that actually this parameter for mu and theta need to be the same. They need to be tied together, which is not too surprising. But when it comes for the alpha, there's this one, which is basically, well, really this is the one that ends up being the interesting thing in the restriction. So I plotted it graphically here. So for the deterministic setting, this is like the t mu and t theta. These are negative values. So think about it like the one choice would be, like I showed in the deterministic setting, where you basically choose -1 for those, and then there's no t alpha at all, 0. So in other words, the alpha k, which I just go back here, you could just put this 1 on top. Versus here, we basically end up putting this k to the t alpha, so it decreases a little bit. We could decrease it a little bit more. So that would be the deterministic choice. This is what I showed you before. In the deterministic setting, though, you actually have a lot more flexibility in terms of choosing those parameters. So we tried to make it as generic as possible in terms of the deterministic setting. When the stochastic setting, though, with these additional restrictions, you have to keep your step size choice in this regime. And basically, you can keep it kind of close to this point over here, but it has to be strictly inside, which is just slightly slower, and you can still get the analysis. So yeah, a lot of details there, but I just wanted to make sure that the main idea of the algorithm is relatively simple. You just have to be a bit careful with some of the parameter selections to make sure that you compensate for the noise while making sure you're getting sufficient decrease in expectation and so on. So what we have here finally is a theorem. Unfortunately, it ends up only being a kind of lim-inf type result. A lot of the things that I've seen for analysis of stochastic algorithms, like stochastic gradient, when you try to prove stronger guarantees, almost sure convergence and so forth, you end up having to use Lipschitz continuity in some way of the gradients and things. And because the barrier, the function itself is the Lipschitz constant is getting worse and worse as you approach the boundary, at least we weren't able to prove anything stronger than this yet. But at least it's still, lim-inf for the gradient is going to go to 0 almost surely. And of course, if you, in any realization, if there's a sequence of xk's that are converging to some point, then it's going to be a KKT point. And this is under, pretty, basic assumptions about, conditioned on the filtration here. You have the expected, gradients or the true gradients. And as I said, there's a bounded noise assumption that we needed, but, be pretty generous, I guess. So let me show you a little bit more experimental results as I finish up here. Again, we're just comparing, there's tons of more experiments we could do, but this is what we did for the paper, just comparing to projected stochastic gradient, or just projected gradient in the deterministic case. So that's the iteration there for that. We just picked some, standard test sets and just basically did one convex and one non-convex problem I mentioned before. So basically logistic regression and then neural network training with these data sets, cross-entropy loss. The performance measure, like I was saying before, but here now I'm stating a little more formally about this relative performance measure between the two algorithms. So this is just a repeat of the picture I had before. So our algorithm, the improvement is down, right? So relatively we outperformed projected gradient. This is within just 100 iterations. If we ran the algorithms longer, they would basically find the same solutions for these problems, and so the difference, the relative performance would be the same. But within a short, budget, a small budget, we're able to get to better solutions faster with the interior point method. This is for the stochastic setting. So for here, we obviously are going to run multiple runs of the algorithm, and here are some box plots here. So Hopefully it's okay, you could see it in the back, but basically, again, we ordered them in some way. There's obviously some problems where it's the performance is varied over the different realization of different runs. But for a lot of the problems, it's pretty consistent across the runs that we had, where the interior point method was consistently better, and this was just within one epoch. So if you have, say, a limited budget here, the interior point method just, within one epoch was getting a better result there. So here, though, by the way, and people always would ask, okay, that's for the training problem. What about for testing? So here, this is the training loss, and then we look at the testing loss between those as well, and there's a better performance for the interior point method there too. And some, this is the non-convex example, and sort of similar conclusions, at least on average. All right, so just to wrap up here, I wanted to, we have been working on the generally constrained case. But I want to just point out, and I don't want to, because we haven't finished the paper yet, I don't want to sort of give away what our ideas are, but I want to explain to you why this is a lot more difficult. Well, first of all, for the bound constraint case, we're basically doing a feasible algorithm. You start with a point within the bounds, and then the algorithm, as an interior point method, is going to stay within those bounds through the entire run. So when we go to the generally constrained case, we could, if we want an infeasible algorithm, things become more complicated. But let's just talk about inequalities only in the generally constrained case. Imagine we just wanted to maintain a feasible algorithm. The challenge comes in with this neighborhood enforcement. Yes, partly because the constraints are nonlinear. That's one issue. But another thing that we find is that when you have this more general setting, is that the constraints start to work against each other, against themselves. Well, I just have a picture to try to explain that. So what we've seen so far is that if you basically extend the algorithm in a very simple, natural way, if your constraints are something like this, so it's just like linear constraints within here, we have this theta region that you would have to stay within. And it turns out if your iterates are in this blue, then things are fine. But when they get too close, here it's still okay, because essentially if you think about here, the barrier for this constraint is sort of pushing you inside. Over here, the barrier constraint here. But here, it actually would push you in a way that you would go interior. But here, once the angle, and I was really surprised when this happened, once you go beyond 45, within 45 degrees, this barrier for this constraint starts to push you too much into this so that we can now no longer easily bound and get sufficient decrease with every iteration when we try to bound that gamma k from below. And so that becomes a real challenge that we have multiple ideas that we're working with, but we were trying to think of what's sort of the best one to pursue. There really is this threshold of like 45 degrees, which I was surprised by. And so we have to essentially sort of think about rescaling your search direction or make the search direction computation a little bit more complicated in order to handle this case when the constraints start to push against each other in terms of their barriers. I'll just leave you with that image. We have some ways that we're working on to get around that, but I didn't want to reveal too much before we finish it up. So anyway, it's an interior point method, single loop, for really designed for the stochastic setting, and we have some nice results for the bound constraint case, and we have a paper out that's under review for that, and we're working on the generally constraints now that we hopefully will be finishing sometime this summer. Thanks very much.